Section 4.3 is modeling with quadratic functions. I can model data with quadratic functions. Big ideas here. Any quadratic function is possibly a stretch, compression, reflection, and/or a translation of the parent quadratic function. Three non-collinear points, no two of which are inline vertically, are on the graph of exactly one quadratic function. And standard form is calculator ready. We don't necessarily use our graphing calculators because we don't have them, but it is a lot easier to type in and do things graphically that way. And it is easier to calculate values and to use it to solve. So we don't use it as a calculator ready, but we use it to calculate values a little bit more than vertex form, which is easier to graph. Example 1 is writing an equation of a parabola. A parabola contains the points 0, 0, -1, -2, and 1, 6. What is the equation of this parabola in standard form? Again, remember here we need non-collinear points, which means they can't be in a straight line. If they're in a straight line, we can connect them with a line, they're linear. Any 3 points that aren't in a straight line, though, we can connect with a parabola. That wasn't a very good one, but we can. So that's what we're looking for here. They also can't be in line vertically because then it fails our vertical line test. So here, these are non-collinear, and they are not vertically above each other. So we can go ahead and come up with our equation in standard form. In order to come up with our equation in standard form, we're going to start off with our general standard form equation. Y equals ax squared plus bx plus c. Now, I have 3 points, so each point I'm going to plug into my equation. Keep in mind that this is x and this is y. So I have 0 for y equals a times x is 0, plus b times x is 0 plus c. I'm going to simplify that and just get 0 equals c. I can do the same thing with my second point. Y is -2. A we don't know, but we know x is -1. B we don't know, but x is -1. And c. When I simplify here, I get -2 equals a minus b plus c. And my third point, y is 6. A we don't know. X is 1 squared plus b, we don't know, x is 1 plus c. Simplify and I get 6 equals a plus b plus c. Now I have 3 equations here, my purple, my blue, and my yellow. I can put those together to form a system of equations. 3 equations, 3 variables. Now keep in mind that my purple equation here has c equals 0. I can substitute right away with that, but it won't always be 0 for c, or some number. Sometimes we're going to have 3 equations that have 3 variables and have to go about it the way we did in section 3.5. So I've substituted my 0 in for my c here. So my system that I have left is -2 equals a minus b, and 6 equals a plus b. So again, the only thing new today so far has been this very first step where we substitute in our values and get our equations. Once we have our equations, we're going to solve them exactly like we did in chapter 3, section 5. So if you need to, look back at those notes about how we solve systems there. Okay, now I have opposites, so I can go ahead and add them. And I get 4 equals 2a, divide a equals 2. Now that I know a, I can find another variable by plugging into one of my equations. I'm going to plug into this one here. 6 equals 2 plus b. B equals 4. And c equals 0. So the only other thing that's different today is instead of writing them as an ordered pair like we did in section 3.5, we're actually trying to come up with the equation in standard form. So we're going to plug our a, our b, and our c into our standard form equation. Y equals, instead of an a here, I have 2. instead of b, I have 4. And instead of z, I have 0. And we wouldn't necessarily need that 0. So y equals 2x squared plus x. 2x squared plus 4x. The 4 was our b value that went in for b, and I was left with the x here. Sorry, not a b. Now feel free to pause here and give this a try if you'd like. We want to know what is the equation of a parabola containing these points. So we're going to start off with our standard form equation. Y equals ax squared plus bx plus c. I have 3 points, so I'm going to plug each point into my standard form equation. Y equals a, we don't know, but x is 0, plus b, we don't know, x is 0, plus c. I'm going to reduce that and get 0 equals c. My second one here, y is negative 2, a we don't know, x is 1, b we don't know, x is 1, and c. Simplify here. And my third point. Y is negative 4, a we don't know, x is negative 1 squared, b we don't know, x is negative 1, and c. Okay, now once we get to this step right here, we have a system of equations. 3 equations, 3 different variables. We can put them together here. And I have negative 2 equals a plus b plus c. Negative 4 equals a minus b plus c. And 0 equals c. We can substitute first. And I get negative 2 equals a plus b. And negative 4 equals a minus b. Again, once we get to this point, we solve it just like we did in chapter 3. So if we have 3 equations instead of one of them already solved for a variable, we set 2 of them equal to each other and go from there. And again, if you need that, there are videos up for section 3.5. We have opposites right away, so we can go ahead and add. And we get negative 3. Now that I know one of my variables, I can find another. So I have A, B, and C. Again, now we get to the last new thing. So the very first step is new, the very last step is new. We plug this into our standard form equation. We keep our x squareds and our x, and we plug in our a, b, and c values. A is negative 3, b is positive 1, so plus 1x, and c is 0. So we get y equals negative 3x squared plus x. So again, this step is new, plugging in our values is new, but once we have all those values, we solve it the same way that we've been doing. So that part's not new. The only difference is we have to come up with our equations using our standard form equation, and then we plug our values back into our standard form equation instead of just into an ordered pair. Example 2 says, campers at an aerospace camp launch rockets on the last day of camp. The path of rocket 1 is modeled by the equation h equals negative 16t squared plus 150t plus 1, where t is time in seconds and h is the distance from the ground. The path of rocket 2 is modeled by the graph on the top of page 210. I also have that here. We want to know which rocket flew higher. So, we can figure out from our graph about how high rocket 2 flew. Keep in mind that that's going to be our maximum height right here. And that point, I'm a little off center there, that point is called our vertex. So our maximum height here is the y-coordinate of our vertex, which is about 580, let's say, or 575. So rocket 2 flew about 580 feet. To figure out how high rocket 1 flew, we're going to have to calculate, because here all we have is an equation. So we can come up with our vertex by finding our axis of symmetry first, which is x equals negative b over 2a. So negative b, a, c. Negative 150 divided by 2 times negative 16. Here, my axis of symmetry is going to be about 4.6875. So x is approximately 4.7 seconds. Keep in mind, my x value is my time, my t. Now, if we plug that back in, that's also the x-coordinate of my vertex. So I can find the y-coordinate of my vertex by taking negative 16 times my x value squared plus 150 times that x value plus 1. So if I take negative 16 times that x value squared plus 150 times my x, and I'm using the second answer key to get that exact value, but you could use the rounded one, and since we're just approximating the height off the graph. And here I get about 353 feet, or 352.5625. So my height for rocket 1 is about 353 feet. So which rocket flew higher? Rocket 2. Now, feel free to pause and give this a try if you'd like. And we're looking for which rocket stayed in the air longer. So, which one stayed in the air longer? Here we already have a bunch of information, so I'm going to flip back so we can look at this. Our graph here tells us that rocket 2 stayed in the air 12 seconds. Started at 0, went to 12. So rocket 2 stayed in the air 12 seconds. We can figure out how long rocket 1 stayed in the air because we found the vertex, which is our maximum value, and that happened at 4.7, which means the distance on the way up was 4.7, so the distance on the way down is also 4.7. So if I take that 4.7 and double it, it gives me about 9.4 seconds. So which one stayed in the air longer? Here we have rocket 2 again. Now we want a reasonable domain and range for each model. So domain, remember, is our x's. So for rocket 1, our smallest x value is 0. And all of our x values are in between there, and we said this was about 9.4 seconds. So our time is always between 0 and 9.4 for it to be in flight. Our range is our y's. Our smallest height was 0. And our biggest height, we said, was about 353 feet, or 352.5 something. Okay, so our height is our y's, and our height ranged from 0 all the way up to 353, and back down to 0. Same idea here for rocket 2 from our graph. We can see here that our domain is our time because it's on our x-axis, and our values are just between 0 and 12. So 0 is less than or equal to our time, which is less than or equal to 12. And our range is our height. We can see that's anywhere here. So 0 is our smallest height, and our maximum height is 580. Quick recap here. Any quadratic function is possibly a stretch, compression, reflection, and/or translation of the parent quadratic function. 3 non-collinear points, no 2 of which are in line vertically, are on the graph of exactly one quadratic function. Remember, non-collinear means we can't connect them in a straight line. And standard form is calculator ready or calculation ready. And that's all I have for section 4.3.